Okay, in today's notes, we're going to take a look at systems of equations. Again, a little bit more review from Algebra 1, but a system of equations occurs anytime you have more than one equation. Anytime you have more than one equation, you ultimately have a system, and the solution to that system is going to be the point or potentially points of intersection. Right now we're just going to be discussing system of equations with two variables, so we would just have two equations. Later on we'll be talking about systems of equations with three variables, and then we would have three. So system is just more than one equation, and then the solution is going to be the point or points of intersection. Where are they equivalent? So let's take a look at some examples. So we're going to find which of these are solutions. Remember, solutions are points of intersections to these equations. So a couple different ways I could do this. I could rearrange both of these for y. So on this one I could just bring the x over here. So negative x plus 1. And then this one I need to bring over the 2x and then flip the sign. And then I could graph these two. I could do that pretty easily on a calculator. We'll go to y equals, I'll put negative x plus 1. And I'll also plot 2x minus 11. And it appears as though they have a solution right there. I could find that on my table. And what I'm looking for is when do these share the same value. And I saw it looked like it was somewhere just over in the positives of x's, and it was a negative y value. And I see that actually occurs right here, 4, negative 3. So that is my correct answer. Also, without solving for y or putting it in slope-intercept form, when it's multiple choice or you have options here, all I really have to do is check these. So if I check this point first and plug it in, I have 2 plus 3 equals 1. Well, that's not even a true statement, so I know that that point does not exist on this line. And I could try this one. 1 plus 1 equals 1. Again, not true. So this coordinate does not exist on this line either. So the only one that works is 4 minus 3 equals 1. So I do know that that coordinate is on this line. And I'll check it in here. 2 times 4 minus negative 3 equals 11. Now that's 8. Minus and minus is plus. And that one checks as well. So this point exists on both functions. So we have a solution to the system. And as we just saw in the system up above, the graphical solution is just the point of intersection. And some different ways I can make my calculator find it. I showed you how to do it on the table here. I just put those in the y equals, second graph takes me to the table, and I look for the common value. I can also make my calculator do it by going to my graph window. And as long as I can see this point of intersection, I go second, calculate, and I want to find number 5, the intersection. And this is just an enter, enter, enter as long as it's in the viewing window, and it will find that coordinate for negative 3. Pretty easy on a graphing calculator. And looking at this one, we're going to do the same thing, solve it by graphing and then check algebraically. This one I can go ahead and plot on my line here, or I can just throw down some coordinates. All I need is any 2 points. I could plot this one, but I see the intercept is actually down here at negative 18, and I can't go that far off the graph, so it might just be easier just to pick some coordinates. So if I plug in, say, 0 for x here, That all cancels and leaves me with y equals negative 18. That's no good. That's the intercept. So let's pick something maybe like 2. So at 2 on x, so somewhere here, that horizontal positioning, 4 times 2, that's 8. And 8 take away 18 is negative 10. So when I'm at 2 on x, I'm at negative 10. So there's 1 point. All I need is 2, and I've got a line. And since I know the slope is positive, and I can use that to find the next point, that's a slope of 4. So I'm just going to come from here and go up 1, 2, 3, 4, and over 1. And I have my 2 points. I have my line. And then we'll plot the second one. This is already in almost standard form, really. Except this should be a positive and out in the front. But what I can do is use this to find the intercepts. So I can plug in 0 for x, find the y. Sorry, this keeps looking like an x. And then plug in an x, or plug in 0 and find the x. So if I plug in 0 for x, this cancels, and I see 4y equals negative 20. I just divide both sides by 4, and so y is going to equal negative 5. I do the same thing here with the y value. I'm going to make it a 0, so that would cancel, and I just have negative 3x equals negative 20. Divide by negative 3, and I get a positive 20/3. So that's not a great point there for the intercept, but let's plot this one. So 0, I'm at negative 5. So there's 1 point. And then 20/3, that's going to be just under 7. That'd be somewhere right about here. So it's going to look something like that. And this one, I know the slope should be 4, so 1, 2, 3, 4, and over 1. So it should actually go through right there. So I'm betting that 4, negative 2 is my solution. Well, let's check. All I have to do to check these is make sure that that coordinate is on both functions. So I'll go ahead and sub this in. So I have negative 2 equals 4 times my x value minus 18. And I know that 4 times 4 is 16. Take away 18 is negative 2, so that one checks. I'll do the same thing here. 4 times negative 2 minus 3 times 4 equals negative 20. And this is negative 8 minus 12, and that is negative 20, so that also checks. I could also solve both of these for y and graph them in my calculator, and again use it to find the intercept. When we classify them, it doesn't have to be difficult. We can kind of break these down into pretty simplistic terms. Really what they mean is when I have consistent systems of equations, that just means that there is a solution. And that could be either one solution, like that, or it could be anytime I have, kind of tough to duplicate, but anytime I have, say, coinciding functions, where it is the same line, one on top of the other. So that would have infinite solutions. Those are both considered consistent. Conversely, inconsistent has no solution. Independent, well, that really just means that they have one solution. And then dependent means they have infinite. And if you think about any two lines in a plane, they're always going to intersect at some point, except for this no solution here, inconsistent, which would have to be parallel lines. That would be an example of inconsistent system. And over your mathematics career, we've talked about a few different ways in which you can solve systems. Really, we've already looked at how to do it by graphing. Then we also have a substitution and an elimination method. So let's look at this problem and use the substitution method. So in the substitution method, we basically just solve for really any variable and substitute it into the second equation. So in essence, what you're doing is you're solving for a single variable, and then you're replacing in the second equation that variable and ultimately reducing it down also to just a single variable equation. Here's what that looks like. So this one's already solved for x, so now wherever I see x, I'm going to go ahead and replace it with 3y. So now go ahead and distribute through here, so this is 15y. And y is 1. Once I have the y, I'll go ahead and plug it back in. Here obviously is the easiest one. 3 times 1 is 3, so x equals 3. So that should be my coordinate, 3, 1. We'll go ahead and sub those back in and do just a mental check. I already checked that one, that's how I got it. 5 times 3 is 15, plus 2 times 1 is 17. That checks as well. And then if we want to solve it graphically, again, rearranging the y equals, I'll do that on the next one and solve it graphically. This one again is already solved for y, so now I will replace y with 2x plus 1. Combine your like terms. Negative 2x is 6x, this is 4x. Subtract 3, and that's going to leave me with 8. And I have my x value. I sub it back in and find the y. So 2 times 2 is 4. So I should get 2, 5. And that should be really my coordinate. And I can double check those. Negative 2 times 2 is negative 4, plus 3 times 5 is 15, negative 4 and 15 is 11. So that checks as well. If I want to graph this, again, I need to solve this one for y, so I add 2x divided by 3. This would be y equals positive 2x over 3 plus 11 thirds. So that's my equation. I'll just pull up the calculator here and we'll take a look at it. So 2x plus 1. And then this one will clear out. Again, if you want to do fractions, alpha y equals a great way of putting in stacked fractions. 2 thirds x plus alpha y equals 11 thirds. And we'll graph it. And it should occur somewhere right about here. I see it does. I can double check it again on the table. Second graph, 2, 5 looks good. I can also make the calculator calculate it. Second trace, that's the calculate function. Number 5. Enter, 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 and there we see it again. And just a couple more examples here, and then we'll take a look at the elimination method. So now a little extra step here. I need to solve for one of the variables. So I'll solve for this one because I just have a single x by adding 6y to both sides. So x equals, we'll say 6y plus 5. Now I take this and replace it in here for x. Distribute that, 12y. And 12y, take away 12y, those cancel. I get 10 equals 10. This happens when it's a true statement, which means any value for y makes that statement true. So my suspicion would be then that these are coinciding lines. So let's take a look. So solve this one for y. And I have, let's see, take away an x from both sides. Divided by -6. Negative over negative is positive, so that's 1/6 x minus 5/6. And we'll do the same thing to the second, solve for y. What you'll see is we should end up with the same equation. Erase some of this here. So take away 2x. Divided by -12. Negative over negative is positive. 2 over 12 is 1/6. Plus 10 over -12, 5/6. You'll see in this case we end up with infinite solutions again. And I came to that because I ended up with an equation that resulted in any value of y making the statement true. So that led me to believe that these were coinciding, meaning an infinite number of solutions. And this one we'll go ahead and just omit for now. It follows the same properties, but it is not a nice number. It's a nasty number. So we'll go ahead and leave that. I won't give you anything like that on the assessment. The elimination method is very similar to old school stacked addition. And you will go ahead and multiply one equation to create an opposite. And here's what that means. So I have 4x, 2x, -3y's, positive y's. I'm going to go ahead and manipulate this one by a 3 just because I already have the sign here. So I multiply both sides by a 3, and I rewrite. So that's going to make this 6x plus 3y equals -24. So that one's gone. That's just one of your properties of equality. It maintains its balance because I did the same thing to both sides. Now this is just stacked addition. 4x, 6x is 10x's. The 3's cancel, and I have 4 and a -24. That's -20 divided by 10. And x is -2. Then I substitute that back in to solve for y. So that's -8. Add 8 to both sides. I get -3y equals, add 8, 12 divided by -3. And I get -4. So I have the coordinate -2, -4. This one, we can really do the same thing. I'm going to go ahead and rearrange it to make it in essentially standard form. Bring this guy over. And I'm going to multiply this one by 2. It doesn't really matter what you do as long as you create the opposite. So this one's going to be 4m minus 2n equals -2. These are both gone. These are my two new equations. Stacked add, 7m cancels, 28, divide, and m is 4. I'll go back to one of these, or I can go back to one of the originals. Sub in 4. If m is 4, that's 8. Minus n equals -1. Subtract 8, that's -9, flip sign. And n is 9. 2 more examples and we'll be done. I'm going to go ahead and multiply this one by a -2. So that's going to create -2x minus 4y equals -8. That's gone. Stacked add cancels. negative 4y, negative 3y, negative 7y equals negative 7. And y is 1. There's one of them, sub back in. We'll just take this one. 3 times 1 is negative 3, so 2x minus 3 equals 1. Add 3, 2x equals 4. And x is 2, so your coordinate 2, 1. And we'll do the same thing here. These ones are already set to cancel. Those cancel. 4r, 20. There's r. I'll sub back in. That's capital R. So this is 5. 5 minus 4r equals 17. Subtract 5. And little r equals negative 3. Okay, so this should be pretty familiar with it. We're still review from Algebra 1. Next section we're going to go on to is systems with 3 variables, which you may or may not have gotten to in Algebra 1. So have your note sheet completed, and we'll get some more practice tomorrow.